Okay, so the last talk of the day is going to be by Beth Ruskai on local additivity.
Okay, I would like very much to thank the organizers for inviting me to give a talk. It's a great honor to speak in memory of my colleague Dennis Petz. So I'm going to talk about a project that relies critically on two results of Dennis's. And first I'll give some background, and then I'll talk about the numerical strategy and the specifics of three-state cubic channels, and then I want to sketch the proof of local additivity, and I will probably skip the numerical issues so we don't all fall of heat exhaustion. Okay, so some time ago in the early days of quantum information theory, there were a number of additivity conjectures, including minimal output entropy, two about entanglement of formation, depending on whether you started with entangled or product states, and the whole level capacity, which is the capacity for transmitting classical information using quantum states and allowing entangled measurements at the end, but requiring products at the beginning. And it was widely believed that all of these were true, and the focus shifted to the minimal output entropy as the simplest to look at. And then in 2007, Hayden and Witter proved superadditivity of a related quantity, the minimal output Rénye entropy, but they left the question of p equal to 1 open. And that was resolved 2 years later by Matt Hastings, who proved the superadditivity of minimal output entropy, and hence the falsity of all the previous conjectures. And that was followed rapidly both by estimates of the violation and other proofs. However, all of these proofs had absurdly small violations in large dimensions, and they were also existence theorems. And I remember giving a talk about this when we thought the additivity conjectures were true, and a physicist said, well, why are you bothering to prove something that everybody knows is true? And my answer was, well, if we can't prove it, then there's something fundamental about entanglement that we really don't understand. And I feel the same way. If we have only existence theorems, which are wonderful things mathematically, but we don't have any specific examples, then there's still something that we don't understand. And what I want to convince you of is that we really shouldn't be looking at the minimal output entropy, but the capacity. And at first glance you might think, oh, the capacity is so much more complicated. But due to one of the results of Dennis Petz, we don't need to compute the capacity. We just need to find one input for which the relative entropy distance from the known product output average is bigger than n times the capacity for a single use. And the numerical effort involved in doing this is comparable to computing the minimal output entropy. Moreover, Gore and Friedland showed that the minimal output entropy, although it's superadditive, is locally additive. Okay? And that argument extends to the relative entropy with respect to a fixed product state. So any local optima from entangled inputs is strongly suggestive of superadditivity. Moreover, we can actually find evidence of violations of additivity even if the actual violation is less than the numerical precision that you can see. So for qubits, we do not expect that the minimal output entropy will be additive, although even this has not been proved for all channels. But there are qubit channels in which the capacity is achieved with 3 non-orthogonal inputs. So that means you do better encoding classical information in 0, 1, 2 in 3 non-orthogonal states, even though you're essentially in a 2-level system. And these seem to me good candidates for testing for superadditivity. Okay. Now, probably everybody here knows the definition of entropy minus the trace of rho log rho. The relative entropy is traced rho log rho minus rho log gamma. The capacity is basically the supremum over all ensembles, the entropy of the average minus the average of the entropy. And it's a theorem first proved by Dennis Petz in collaboration with Oya and Watanabe that you have an alternate expression for this, which is a min-max theorem. It's the inf over all gamma of the max over rho of the relative entropy phi of rho phi of gamma. And if you have the true output average here, then it's just the max over all rho of the relative entropy with respect to phi of rho and phi of gamma. Okay? And it's this result which will allow us to show additivity violations, I hope, with the same numerical work as computing the minimal output entropy, and I think more hope of success. Why do I think that? Well, first of all, if we have superadditivity, then if we look at this expression, the max over all states gamma of the distance from the optimal output average tensored with itself n times, and this is something that we know, and we know to arbitrary accuracy in practice. Well, this max is bigger than or equal to the inf over all gamma here, but by the max-min formula I had, this is actually equal to the whole Lowell capacity, and if we have superadditivity, then that's bigger than n times a single use. So if you have superadditivity, then we know that we have this inequality for at least one entangled state. Moreover, if that inequality holds, then the tensor product of the output averages is not the optimal average, okay, which implies superadditivity. So we don't need to find the capacity, and we don't need to find the new optimal average, okay? All we need to find is one entangled psi that satisfies this inequality. And the second term in the relative entropy is something we know from a single use for arbitrary accuracy. So the numerical effort is basically essentially the same as looking for the minimal output entropy. Now, why do I think there's more hope of success for this? Well, for one thing, the Gore-Friedland argument that minimal output entropy is locally additive extends to the relative entropy with respect to a Fisk's reference state. Moreover, maybe I should go back. This min-max formula implies in particular that the optimal outputs are equidistant from the optimal average. In particular, that implies, since this is additive, that the inputs for the products of the inputs for a single use, or the outputs from a single use, are equidistant from the product average. Okay? So superadditivity has to arrive from entangled inputs that satisfy this inequality, that they're bigger than n times the capacity with respect to the two optimal average, and they'll be equally distant from this with a larger radius. Okay? So what we expect is that there are also local maxima with entangled inputs with respect to this product average. Okay? So let me show you on the next slide, I hope, a picture. So in the red at the center, we have the products of the optimal output averages, and we know there are some local optima here with the red diamonds that come from the products of the single-use inputs. We also know that if we have superadditivity, the blue is the true optimal average output, and there will be some local maxima denoted by x's, okay, with respect to this. And we expect that slight perturbations of this, which I had green before and you couldn't see it, so I switched to brown, but it doesn't look like you see brown. But we expect that when you measure from the product, which we know, that there will be perturbations of this which are also local optima. And some of them will be closer in distance here than what we want, but we know that there's at least one that's going to be further outside the red circle. So we're not, unlike the case of looking for minimal output entropy, we're not looking for a needle in the haystack to find that one entangled state that gives us superadditivity. What we're really looking for is, in this region in between, an annulus of local maxima, some of which come from products and some entangled inputs. And from the channels I'm going to propose, it's very easy to distinguish the product inputs from the entangled inputs. Moreover, even if the violations are outside the numerical precision, it's almost even better. Because if it's outside the numerical precision of what we can see, these two pictures will coincide. Numerically, the product average and the true average will be the same, and we'll have these red diamonds, which are local optima that come from product inputs, and then we'll have the X's, which are local optima that come from entangled states. Okay? So we have this interlaced picture of product and entangled local optima that we're looking for. Okay. Now, the channels that I suggest using are ones that I found some time ago with Chris King and Michael Nathanson. They're qubit channels, which I call three-state capacity. So in the block sphere representation, that maps to an ellipsoid, and I will assume that you just shift in one direction orthogonal to the longest axis. And the idea is I'm going to consider some restricted capacity, CV, in which the inputs are the north and south pole, and with some probability, and I'll call that capacity CV and the optimal average rho Z. And I'll have another restricted capacity that I'll call CH, where the inputs are restricted to be on a horizontal line. So plus or minus X and some Z. Okay? And I'll call that rho H. Okay? Now you can definitely tweak the parameters to make these two constrained capacities equal. Now I want to take the average of these two ensembles, okay? And when you do that, the entropies from the optimal inputs will all cancel out, and if you look at the difference of C4 minus, and this is really C2 since these are equal, well, you'll be left with the entropy of the average of rho V and H minus the average of these two entropies. And if rho V is not equal to rho H, then this will be strictly positive by the strict concavity of the entropy. So this four-state ensemble we know does better. Now it turns out that because of the symmetry, we chose mu1 equal to 3 states do even better. Okay? And we can check numerically that this condition holds. Okay? Okay, so we have these symmetric 3-state channels. We also have 4-state channels. And here's a diagram of the first one we found showing the optimal inputs. Notice in this example, the north pole is a fixed point. And then these inputs, the optimal outputs are here. Okay. Now, there's a problem with trying to do calculations with that channels because we let the shrinking of the x and y, sigma x and sigma y, the optimal inputs, you have the north pole, and then you have the horizontal inputs at some z plus or minus the square root of 1 to minus z squared. But actually, that's all you need, but you actually have an entire circle at latitude z. Okay? So you only need 3, but you actually have a lot more, and when you take a tensor product, that gets very complicated. So looked a little bit with Ben Krieger at IQC. There are 4-state channels that were found by some people in Japan. The problem with that is that the 4-state channel was really just a perturbation of the 3-state channels. And this is a heat diagram. The red is the relative entropy distance from the optimal output average. This is just for a single use. And for a single use, we had trouble finding the relative optima when we used the algorithms we were going to use. The point is that you had a memory of this circle, and you could quickly get up to this red ridge, but then it was very, very flat, and it was hard to find the peaks. So, what to do? Well, we didn't really need all those circle of optimal inputs, so we can get rid of them just by setting the coefficient of sigma y to be 0. The problem with that is you no longer have a completely positive channel. So, you can tweak the parameters to find good CP channels. Okay, here's the complete positivity condition. you need to make mu3 plus T3 strictly less than 1. And that's something numerically you want to do anyhow. You don't want to have a pure output because then you have 0 eigenvalues and the computer will not be happy. And so you just make it a little bit smaller, like 0.95, and then you can easily make mu2 less than mu1. And you don't need it to be 0, you just need it to be smaller than the coefficient of sigma y to make it undesirable to go in that direction. Okay? Another advantage is, going back to three-state channels, is they're working in the xz plane, so everything is real. Okay? So here are the desired properties for good three-state channels. There should be no pure output. The advantage should be at least 10 to the minus third. In the 4 states, we're only 10 to the minus fourth. Mu1 bigger than mu2 is easy. And we'd like to have relatively steep peaks in some sense. And we would also like to preserve entanglement in some sense. Now, all channels of the type I'm describing are not entanglement of breaking. So I looked at the entanglement of formation of the Choi matrix and did some preliminary calculations. And once you have mu3, mu1 is determined by the CV equals CH condition, and then you make mu2 as small as you can without violating the CP condition. And once you get up to mu3 equal to about 0.7, you basically get close to this C3 advantage of about 10 to the minus third, and it's not very sensitive. And the peaks get a little bit sharper, but that's not terribly sensitive. But as mu decreases, the entanglement of formation rapidly decreases. So it looks like you want something roughly around mu equal to 0.65. And here's a plot of the relative entropy distance from the optimal average for a single use for those values. And you see it looks like the peaks are pretty good. Here's sigma y. This isn't terribly sensitive to the parameters. This gets better as mu decreases, but this is certainly more than enough. This is going around in the xy plane at a fixed z to ensure that you can stay in the xz plane. Okay. So basically, we're looking for many entangled local maxima of this relative entropy distance, and we need to be able to distinguish entangled inputs from product ones. And that's the other advantage of the three-state channel. We know the form of the inputs. They're either the north pole or plus or minus a, 0 square root of 1 minus a squared. And so if we have products of these, we can determine that simply by looking at the coefficient of sigma x tensor n, which is basically the trace of the skew diagonal of the input. And if it's 0, then psi is a product of the north pole with something. It may be a product of optimal inputs. If it's a product of something entangled, then we should have seen violations earlier. And if it's a product of these inputs, it will be plus or minus a to the n, and this is something we can determine to arbitrary accuracy. So it's very easy for these channels to distinguish the entangled inputs from the products. We don't need elaborate tests of entanglement. And so we're not looking for a needle in a haystack. We are literally looking for a haystack of entangled inputs that satisfy a certain, that are local optima. And we can find them even if the capacity is beyond the numerical position. And this all depends critically on the fact that you do have local additivity. So now I want to discuss the proof, and this is joint work with John Yard. So Gore and Friedland showed that if you look at the inf of the entropy of a channel phi of A, rho A, and has 2 local minima, then the tensor product also has a local minimum at rho A tensor rho B. Okay? And this extends to the minimal output entropy with respect to a fixed state. Okay? So if you look at, if you have a local maxima at rho A tilde, rho B tilde, and you look at the relative entropy output with respect to the product of the optimal, of the fixed outputs, then this will also have a local maximum at rho A tensor rho B. Okay. So, the first step is to reformulate the problem using the Stein spring representation, and I won't go through this in detail. I think people are familiar with it. It's just mostly notation, but basically the minimal output entropy of a channel phi is equivalent to the inf of S of XX dagger, where X is a dB by dE matrix in some subspace, and the channel determines the subspace by the Stein spring representation. Okay, so we can look at this equivalent problem. All right. Now, a critical point is that we generally will not have square x's because the environment and the output will not be equal. But for any x, we can have its polar decomposition, and there's a variant. You could also write square root of xx dagger vb. And I can write x as pb x pe, where these are the projections onto the kernel of xx adjoint and the kernel of x adjoint x, respectively. So we'd like to show that it suffices to consider y in this subspace. So given an x, okay, that we know, okay, that if we think it's a local optima, to show whether or not it's a local optima, we don't have to look at all possible x's, we just need to look at those in this subspace. And the intuition for this is, in the Schmidt language, if you perturb a state by something that's orthogonal to where the Schmidt states have non-zero coefficients, then you typically get something that's more entangled. That's true for sufficiently small p. Obviously, if t equal to 1, you could end up with a pure state. The intuition is, if you look at this in block matrix form, well, if the y piece is completely orthogonal to xx dagger, and I'm assuming that this, bad notation, but it's strictly positive. If you make t sufficiently small, the largest eigenvalue here will be smaller than the smallest eigenvalue here. So the eigenvalues of xx dagger will majorize the eigenvalues of this quantity, and xx dagger will be smaller than the entropy for any perturbed state. This does not hold for arbitrary y. Putting y here doesn't cause any problems, but the cross terms here do. And so I'll have to go back to the proof of that after we know some expressions for the derivatives. So differentiation is straightforward if you use the integral representation of the log. And for this, it's necessary to assume that rho is full rank. If rho is not full rank, I would have to replace the identity here by the projection onto the range of rho. So the derivative of the logarithm can be written using the integral representation as the limit as epsilon goes to 0, the integral 1 over rho of t plus ui minus 1 of rho of t plus epsilon. And you can put these over a common denominator. This step is very easy, but people often seem to find it mysterious. So if you have A inverse minus B inverse, I can write that as A inverse B inverse minus A inverse A. And it's importantly important. It's important that the B inverse is on the right and the A inverse is on the left, because now I can factor out an A inverse and a B inverse, and I just have B minus A. And here, when I take B minus A, the ui's cancel, I end at rho plus t plus epsilon minus rho of t. If I take the limit inside, I got the integral from 0 to infinity, rho of t, rho prime of t, 1 over rho plus t. And some people will recognize this expression as the symmetric logarithmic derivative. I'll come back to that later. So we have this expression for the derivative of a logarithm. That makes getting the rest of the derivatives easy. First thing to observe is that the derivative of the log, which is what's under this integral sign, is orthogonal to rho of t, because if I multiply by rho of t and take the trace and use the cyclicity of the trace, then these all commute. I can do the integral, get rho inverse, and I end up with the trace of rho prime, which is 0. And now I can differentiate just being careful using the usual formulas as long as I'm careful about the order. So you have minus the trace of rho prime log rho of t minus the trace of rho, the derivative of the logarithm, but we just saw that this is 0, so we just have this expression. If we differentiate again, we minus trace of rho double prime of t log rho of t, and then we have minus trace of rho prime, this expression for the derivative of the logarithm, this integral. Okay? And now if we go back to our matrix picture where rho of t is square root of 1 minus t squared x plus ty, then basically rho prime of t is going to be yx adjoint plus xy adjoint. Okay, so we have minus trace of that, log, and rho is xx adjoint. For the second derivative, the rho double prime, I'll have a yy adjoint here minus xx adjoint. With the log of x, the x becomes the entropy, and I have minus trace yy prime, and then we have minus trace of this quantity, which I'm calling gamma 1, and the integral again, 1 over xx adjoint, gamma 1, 1 over xx adjoint. Notice that the integrand is a positive semi-definite, and when you take the trace, no, the integrand is not, but the gamma 1 times this is positive semi-definite. And then this is positive semi-definite. So this is a positive quantity, but we've got a negative sign. This is negative, minus the entropy is negative. So if we have a local minimum, it's all going to have to come from this quantity being positive, minus the trace of yy adjoint, log of xx adjoint. Okay. Now, I want to rewrite these formulas using left and right multiplication. So left multiplication of A acting on W is just A times W, and right multiplication is just W times B, and these commute even if A and B do not. And the relative modular operator denoted delta A is left multiplication by A, right multiplication by A inverse. The relative modular operator was defined by Araki, I think, in 1976 plus or minus 1. And his original motivation was to extend results like strong subadditivity to type 3 von Neumann algebras, which don't have a trace. And for a long time I thought this was some technicality, and it was really the influence of Dennis Petz who realized that the relative modular operator could be useful, extremely useful, in finite dimensions, okay, and in particular in quantum information theory. So, if I write x as square root of xx adjoint v, then I'm going to define v y adjoint. If x were self-adjoint, I would just have y adjoint here in the middle, w minus iz. So w is the real part of v y adjoint, and z is basically the imaginary part. And notice that if we have x square, okay, then you can just put the v with the perturbation and assume that x is self. So if you can get x to be square, making it self-adjoint is easy. And then gamma 1, which is x y adjoint plus y adjoint x, it's just x w minus iz and w plus izx. And now if you look here, you have x w plus wx, so that's left multiplication by x plus right multiplication acting on w, and the imaginary part we get a minus sign, and I define m plus or minus to be lx plus or minus rx. So now if we go back to our derivative formula, I'm just going to look at the last term, which is the one that's not additive, which is problematic, and I'm now assuming that x equals x adjoint, so I'll just write x squared. And I put in what I have for W1, the m plus W minus I m minus Z. I'd like to move the m plus over here and have a W on the left, and the same thing here. With the plus, you get a plus sign. With the minus, you get a minus sign. That means the imaginary parts cancel out, and you get this expression, trace W m squared W, and here we have m minus squared. And you can cancel an m plus here and an m minus here. All of these multiplication operators commute. And you end up with this expression W, relative modular operator delta this should be delta x squared. Delta x squared plus I, delta x squared minus I. No, it's just this one is just delta x. Here it's delta x squared. Sorry, this one is just delta x. This is delta x squared. And here you have the minus sign on top and on the bottom, and I can write that as trace w phi of delta x w plus trace z phi of minus delta x z, where phi of a is this defined to be a plus 1 over a minus 1 log of a squared. Okay, so we have this expression. Now that's very useful. So now if we put this back into the full expression for the second derivative, we have the entropy term minus trace of y adjoint log x squared, and then the integral term has just become this minus trace w phi of delta x w, and with z minus delta x. If I have iy, that just switches w and z. So if I combine these two, okay, and if I have a local minimum, then both of these will be positive, so the sum will be positive. It turns out that phi of a plus phi of minus a is a squared. And here I have a phi of delta x, and here a phi of minus delta x. So I can rewrite this, and then it turns out that I can forget about w and z and put things back in terms of y. Because the Prof I make minus trace phi of delta x squared y adjoint, the imaginary parts cancel out, and I just end up with this, okay, which is very convenient. Okay. And the key inequality of Gore and Friedland was to show that 2 phi of bc is less than or equal to phi of b squared plus phi of c squared. And that's elementary inequality. You can check that if a is positive, it's bigger than phi of a is bigger than phi of minus a, and is bigger than phi of 1, which is equal to 4. So there's no loss of generality in assuming that a, b, and c are positive here. Phi of a inverse, you can check, equals phi of a, so I can just assume they're both bigger than 1, and one has to, if they're equal, it's trivial, so one has to be bigger than the other. You plug in, you cancel out, and you get that the b log b over b squared minus 1 is strictly decreasing. So I can differentiate this function. It's a calculus exercise for x bigger than 1. This is positive, and I just proved that phi of positive number is bigger than 4, which means that this is less than 4, and with the minus sign, and so this quantity is less than 0. So it is indeed decreasing. And then that translates immediately to an inequality for the modular operator, and it's exactly what you need to prove the result for product perturbations that are orthogonal. And it also allows one to eliminate cross terms and reduce the general case to that of products. Okay. The first two terms are additive, so the inequality lets us deal with this last term. It's not additive. This is a subadditivity inequality, so that makes this term superadditive, and I'm going to skip this. And I would like to say a few words about the reduction to square non-singular form, because that's a subtlety, and I thought several times I had a really slick argument, and it's, I think, not very clear in the original paper. Okay. So remember the expression, the first derivative is minus trace gamma 1 of log xx adjoint, second derivative minus 2 trace y adjoint log x entropy, and then we have this term. Now, I'm going to say write x in block form, so this is bad notation. X is now the part that's non-singular, okay? PB, X, PE, zeros here, and the correspondingly projecting for y, and I'm going to write the adjoint of y. And I'd like to say, well, if I multiply this, xy adjoint plus y adjoint x, I get this expression, which is, and then I have x, y adjoint 2, 1, and y1, 2, and y2, 2 never appear, and their only contribution, therefore, is this term, which is strictly positive. The problem with this argument is I derived all of the derivative formula, obtained all the derivative formulas by assuming that x adjoint was not singular. So this would be a very circular argument. Now, before I show you how to get around that, which is to perturb it, notice that if either x adjoint or x adjoint x is non-singular, the result is easy. For example, if x adjoint is not singular, I can write it in block form as x0, and y in corresponding block form really does not contain y2, so its only contribution is to this term, which is positive. And y2 equal to 0 is equivalent to y being in WPE, which is what we want. If x adjoint is not singular, then we can use the fact that the entropy of x adjoint is the entropy of x adjoint x to reach the same conclusion. So, in the general case, what we have to do is where we had a 0, put in some small epsilon times f, where ff adjoint projects onto the orthogonal complement of pb. Okay, so it projects onto the kernel of xx adjoint. Okay. Now, you would like to say, okay, well, we'll just take a limit and hope everything goes to 0. Unfortunately, when you take the limit, everything does not go to 0. Okay. So we have this term with y11 and y22, log x epsilon, that's quite well behaved. And the y21 and y22 terms multiply the part that had this part that had a PB perp, and you'll have a log epsilon squared. You might say, well, that's not so bad, it's going to go to plus infinity. However, we have this integral term with these logs of 1 over epsilon squared plus u, that could go to minus infinity. And in fact, it does go to minus infinity. But what you can show is that for this term, the contribution of y12 to this term does go to 0. The contribution of y22 does not go to 0, but it's finite. Okay? And since this term goes to plus infinity, that will kill that. Okay? So, if y12 and y22 are non-zero, they can only increase the second derivative and hence the entropy. Okay? So, there's no loss of generality in assuming that y12 and y22 are equal to 0. And that's essentially all you need to do. Okay? Because once you've got 2 of them equal to 0, then you're essentially, you can restrict to, you have 2 zeros, you're essentially in a situation similar to what you had when you had xx adjoint or x adjoint x non-singular. Okay? So this is all you need to do. If you do more work, you can discover the contribution of y21, okay, to the last term is indeed minus infinity. So we have trace y21 adjoint log epsilon squared going to plus infinity, but we get exactly the same thing going to minus infinity canceling, and you get minus 2 trace y21 adjoint y21 log x adjoint x, which is exactly what you would get for the contribution of y21 to the entropy if you looked at S of x adjoint x instead of x adjoint. So that's the right thing. Okay, so that completes that. Now I was going to talk a little bit about some numerical issues fast, but I think it's very hot and it's very late, and so I think I will skip. To the end. So the summary is, okay, our search, we're looking for entangled, local maxima, okay? And ideally, we'd like to find an entangled input that satisfies this inequality, that the relative entropy distance with respect to the product average is better than n times the single use. But we really first want to look for a haystack of entangled inputs. And if they're not all equal, then we'll try to refine it to find one that satisfies a strict inequality. But if the numerical difference is too small to observe, okay, we still, okay, get a proof of superadditivity if we have this picture of interlaced, entangled, and product inputs that are local optima. Okay? And now previews of coming attraction a year from now. There are 2 workshops in Bath, one on the many-faceted Kahn embedding theorem and another one on quantum resource theories. And I think that's enough for today.
With more questions and that's very good.